All right, we're gonna go ahead and get started. This is Unit 3, Essay Video 2. Part 1, we're gonna be talking about pressure volume loop. This is the pressure volume loop right here. One whole loop goes through the cardiac cycle once. So I'll explain what's happening within the loop and inside the heart. So first we start right here. This is this bottom part. Well, I guess let me explain this. This is pressure. So as we increase on the y-axis, we increase in pressure. As we increase on the x-axis, we increase in volume. So right here, and this is talking about the ventricle as well, the left ventricle. So right here, we start, and this line right here is the filling of the left ventricle. And so this begins with the opening of the mitral valve or the bicuspid valve. And as it opens, blood fills the left ventricle. And at this point right here, pressure in the, I didn't draw it super well, but there's a slight increase in pressure as it fills. But as we increase in pressure, we finally, the ventricle pressure becomes more than the atrium. And so that bicuspid valve is going to close. And then once it closes, we have this point, and this is contraction or isovolumic contraction. There's no change in volume, but there's change in pressure because there's both those valves, the semilunar valve and the mitral valve, they're closed, but the ventricle is contracting. So there's a closed system, but the pressure, the area is decreasing. So there's a big increase in pressure, and we call that isovolumic contraction. And so eventually, we're gonna have a buildup of enough pressure where the semilunar valve is going to open. And the blood from the left ventricle is going to go into the artery, the aortic arch, or just it's gonna go into the body. And so this is called like the ejection phase. The blood's being ejected into the rest of the body, away from the heart, out of the heart. And eventually, the pressure in the ventricle is going to decrease enough where it's lower than the pressure in the aorta. And the semilunar valve is going to close. And then once it closes, we just have the same amount of volume. But if the semilunar valve is closed and the bicuspid or mitral valve is closed. So we have two things closed. Again, it's like the closed pressure system, but this is where we have isovolumic relaxation. So the ventricle starts to relax, but we have a closed system, but the area is expanding. So that pressure is going to go down. It's like a vacuum getting ready to cause the mitral valve to open to have that passive filling of blood from the atrium. So the right atrium. So yeah, that's the cycle. I didn't really mark the points on here. I think on average, the ventricle has like 50 milliliters of blood in it after it contracts and releases the blood into the aorta. So I guess right before the mitral valve opens, we have about 50 milliliters of blood, and at this point, when it finishes filling, this is usually around about 120. So yeah, that's the loop. I'm trying to think if there's anything else important I want to mention. The closing of the mitral or bicuspid valve, that's our first heart sound. Then we have the closing of the semilunar valve, and that's the second heart sound. Also right here is another important point. It's like the maximal ventricular contraction point. The reason why this point's important is because this is where we get our inotropic line. It starts right here. I can't remember exactly what it is, but it's not quite to the 0, 0 point. We still have a little bit of volume of blood in there. Can't remember exactly why, but I think it's just like, I think in the book it talked about how it was physiologically impossible for all the heart to get out of the blood. And so that's why this point isn't at the 0, 0. Not super important though, I don't think, but pretty much there's this point right here with 0 pressure, but we still have a little bit of fluid, or not fluid, a little bit of blood volume, and then to the point of the maximal ventricular contraction, and we draw a line from there, and that's our inotropic line. And if you remember when we talked about inotropy before, that's like contraction strength of the heart. So yeah, and then if we take our relaxation, isovolumic relaxation, and our isovolumic contraction, the space in between there is stroke volume. And that's kind of where we get 50 milliliters, 120 milliliters. And we subtract those, like 120 minus 50. That gives us 70, so our stroke volume would be 70 milliliters. That's like an average. But yeah, I guess that kind of reminds me of these up here. So within the heart, we just talked about stroke volume, how much volume is inside the heart before contraction, and then how much volume of blood is inside the heart after contraction. And so that's the stroke volume. And then stroke volume, that's like the amount of blood going through the heart through one cycle or one contraction. So we take that, or each beat, that's how much blood's going through the heart each beat. But then the heart rate is how many beats per minute. And so how much blood going through the heart each beat times multiplied by how many beats per minute is giving us our cardiac output. And our cardiac output is how much blood is going through the heart each minute. And then our MAP, or our mean arterial pressure, that is the blood pressure, and that is the cardiac output. So how much blood we are pushing through the heart each minute, multiplied by the peripheral resistance. I need to do a little more study on peripheral resistance. I think that's just the resistance that the vessels outside the heart put on the heart. Like, it's like the resistance the heart has to overcome to pump blood out of it, and all that resistance is coming from other places within the body. But yeah, then there's a couple of other important points right here. We have this point right here is called preload, and preload is the amount of blood that's venous return, amount of blood getting returned from the body into the heart. So if we have a lot of blood coming back into the heart, more than the 120, let's say we have 140 milliliters of blood getting from venous return into the heart, obviously that's going to go up, that's going to increase the preload. Afterload, that is the pressure the heart has to overcome to pump blood into the aorta or into the arteries. So things that can affect this are, let's say this is a healthy individual, someone who has a lot of plaque buildup in their arteries. Let's say, just like right outside of the heart and the aorta, the aortic arch. There's a lot of plaque buildup. That's going to give us a smaller hole, a smaller diameter for the blood to pump blood out into. And so if that's a smaller diameter, smaller area, that's more difficult for the heart to pump blood through that smaller diameter. You can think about if you're drinking through a straw. If you're drinking through a straw that is from a Kool-Aid straw, versus a straw that you'd use to like drink for like a milkshake, one of those thicker straws, it's going to be a lot easier to pass fluid through the thicker straw. That's kind of the same thing here. If we have a smaller artery due to plaque buildup, we're gonna have to increase the pressure to get blood to flow through that area. So yeah, let's talk about these other little graphs we have here, because these are important because preload, afterload, and inotropy all affect this graph. Preload, venous return to the heart. So like we kind of mentioned, let me grab a couple more markers. We have, let's say we increase preload, more return to the heart. Sorry, didn't mean to draw that. Okay, so we increased venous return, increased preload. What does that do to, how's it going?
I have this room reserved.
You have it reserved?
I'll find another one.
Okay, I can leave in a few minutes.
I'll find another one. There's plenty down here.
Okay, thanks man, I appreciate it. Nice guy. I traded that guy beef jerky for a bike once. Okay, so increased preload is going to increase stroke volume, increase the amount of blood being pumped through the heart. If we decrease preload, let me grab another color. Let's use blue. If we decrease preload to right here, instead of giving the 120, we're getting 190. I drew that a little bit wrong. We're decreasing the stroke volume because here is our line with decreased preload. Here's our line for normal preload. And then I'll draw on the bottom here. Here's our line for increased preload. So you can see decreased preload in the middle is going to decrease the stroke volume. Normal is right there. If we increase preload, stroke volume increases, more blood going through the heart. But as you can see with preload, changing preload doesn't affect our inotropic line. The heart's still contracting at the same strength. Yeah, that's how preload affects the stroke volume. It doesn't affect pressure or inotropic line. Next, we're going to go to afterload. And afterload is, like we talked about, you can't really see it. You can see a little bit. It's this point right here. That's like the resistance the heart is receiving from outside of the heart. That's like the resistance the heart needs to overcome to pump blood out of the ventricle into the arteries, into the aorta. So for this, if we change, I want to draw this line actually a little bit longer, a little bit higher. I think that might help. Okay, so if we increase afterload, so instead of going to this point, we go up to right here, and we come over, we're going to hit the inotropic line faster, so we come straight down and back right here. If we decrease afterload, decrease the resistance it takes to pump blood out, go to right here, come to right here. Can't see it super well because my line's not great, but pretty much if you decrease afterload, decrease the pressure it takes the heart to overcome to pump blood out, you're going to increase stroke volume. And the reason why that is because if the heart has to overcome a greater resistance, it's going to spend more of that energy it has to overcome the resistance and pump and open that semilunar valve and pump blood out. it's gonna have less energy to do the full contraction. And so, sorry, I messed that up 1 second. Hello?
Hi Nick, are you ready for me to come pick you up or just be a little longer?
Probably be like 20 more minutes, but you can come now if you want.
24 minutes?
20 more.
Okay, I might eat a little food and then come over.
All right, sounds good. I love
Are you
you.
going home and then go to work or just work?
Probably just work. All right, love you.
Love you.
Bye.
Bye.
That's my 1 subscriber right there. Okay, so back to this. If we decrease afterload, decrease the resistance the heart has to overcome to pump blood out of the ventricle, it's gonna have more energy to contract and contract and push more blood out of the heart. So that's why the stroke volume increases. With increased afterload, it's having to overcome a greater resistance, so more energy is being spent on overcoming this resistance, that it has less energy to contract and push the blood out, so we end up pumping less blood out of the ventricle. And you can see the inotropic line is our guide here, and this is if we have the same amount of contraction from the ventricle. But as you can see, increasing afterload decreases our stroke volume, decreasing afterload increases our stroke volume. Hello?
Hi Nick, a shopping order for $27 just came in. It's like 2 orders. Should I do it or?
That sounds good to me.
Okay. And I can get you after?
Yeah, that works.
Okay. Sounds good.
All right. Love you.
Love you.
Love you, bye.
Bye.
Okay. You see this inotropic line super well? Okay. Inotropy. Strength of contraction, inotropy. Inotropic line tells us what that is. So, the inotropic line all of a sudden goes steeper. Actually, I want to draw a little steeper just so it's easier to see, kind of. Ooh. Nope, not that steep. Right there. Inotropic line steeper. We have greater strength of contraction. Inotropic line less steep. How does that affect these things? I have to look at this just to make sure I'm explaining this right. Okay, I got this. All right. As you can see, with the decreased inotropy, decreased strength of contraction, we only can go to right there. Okay? Stroke volume is decreased, because this is normal stroke volume. Increased contractibility strength, increased inotropy. We're gonna have this line right here, come down right here. So now we have this line that's longer. Increased stroke volume. So increased inotropy, increased strength of contraction, increase the amount of blood being pushed out of the heart, which increases stroke volume. Decreased inotropy, decreased strength of contraction. We have less of the strength contracting the ventricle, less blood's coming out, decreased stroke volume. So that's the pressure volume loop. Grab my markers. Okay. I actually just need this part right here. All right, this is the baroreceptor reflex. This isn't too hard. Baroreceptor reflex is important is because our body's blood pressure can change, and it's a short-term response, short-term fix to change in blood pressure. For example, if we're sitting down, all of a sudden we stand up really quick. Gravity can kind of pull our blood down, and that can kind of make us feel a little dizzy. This reflex catches that and it responds super quick. I think in a video I watched, it was saying that when that change of blood pressure is received, once that baroreceptor picks up on it, within 2 heartbeats, it's the effectors are working to fix that. So it's really quick. But yeah, let's just talk about it. So we have the heart here, we have the aortic arch, and we have the cardioid something up there in our neck. We have these receptors on them, the baroreceptors, or pressure, I think it's like I said, pressure receptors. And those are going to sense change in pressure. Because if more blood's coming through here, increased blood pressure, it's going to stretch it. And when it stretches, it's going to send action potentials and say, hey, blood pressure is high. We're having a stretch, increase action potential. Brain's going to receive it and say, oh, blood pressure is high. So yeah, these baroreceptors are in these 2 places, aortic arch for sure, cardioid, something up there. Glossopharyngeal nerve, number 9, is going to go to the medulla, and there's a center in there called the cardiovascular center. Nerve 9 is going there. I hope this kid's not waiting out here. Okay, cranial nerve 10 is going to come from the aorta, go to the same place in the medulla, the cardiovascular center. And it's going to send whatever it's picking up. Increased stress, increased stretch, increase action potentials, decrease stretch, decrease action potentials. Decrease stretch, low blood pressure, increase stretch, increase in blood pressure. Response, parasympathetic, vagus nerve right in the heart. Vagus nerve only affects like the heart rate. So, because the thing here is, if you remember, MAP is peripheral resistance and cardio output. Cardio output is stroke volume and heart rate. So if this parasympathetic can affect the heart rate, if we have a decrease in blood pressure, or let's say an increase in blood pressure, I'm not sure if it's 100% what I'm about to say, correct? But if we have a decrease, I'm trying to think, because the parasympathetic will want decrease in heart rate or decrease in blood pressure. So we have an increase in blood pressure, increased stretch. The parasympathetic can respond by causing the heart to beat slower, I think, and combat it. I need to look into that a little more. The book explained this, but I feel like it didn't go into as much detail as like explaining, okay, if it's stretched, this happens, that happens. So I may have to watch a video on it. But sympathetic goes through the vertebrae and chain ganglia. It can go to the heart and affect contractile strength. I think it can probably do increase heart rate too. Yeah, it can increase the heart rate. It can go to the atrials and constrict them, because if we have low blood pressure, we want to increase blood pressure, it can constrict the arterioles, and that will increase the blood pressure, help increase it. We can also go to the adrenal medulla and let out epinephrine, norepinephrine, can't remember which one, but it lets out those into the blood vessels, and those will eventually get to the heart, and those will cause heart rate to increase. Yeah, so that's the way the baroreflex works. I know it's a little bit rough, but that's pretty much how it works. Yeah, I think I need to look more a little into exactly how, okay, so the stretch, increase blood pressure, increase action potentials. I think I have that down, sends it here, but it's like, if there's an increased action potentials, increased blood pressure, I guess that would probably mean the parasympathetic is gonna kick in and like decrease the heart rate, which I think. But if we have decreased stretch, decreased action potentials, decreased in pressure, the parasympathetic might wanna raise that, and it can increase the heart rate. It can also constrict the arterioles, and it can cause the adrenal medulla to release adrenaline and norepinephrine. Here's that. Probably need to scoot back a little more. There, it looks good. Okay, let's run through this one. This is capillary. Forgot to draw one thing. We also have cells within the capillary, or not within the capillary, but through the capillary exchange. So this is like the arterioles, the venules, I think they're called. And this is where exchange happens for gases and stuff. I'm pretty sure like the gases and other small things can pass through here. No problem. But there's bigger things. I forgot to write down albumin. There's albumin. And I think that has kind of to do with BCOP, but we have albumin. So we have albumin. Okay. Let's start here. This is a sphincter, a precapillary sphincter. And if we have increased blood pressure, we have more blood coming through, that's going to push on these sphincters, and it's going to cause them to contract, to decrease the amount of blood coming in. Because there's a couple different factors that affect this precapillary exchange. But also if there's decreased blood pressure, there's decreased stretch on this, they're gonna relax more, allowing more blood to come through. I'll talk about why that's important in a second. So we have hydrostatic pressure. That is the amount of pressure within this capillary. And if there's a really high amount of pressure, it's gonna push more fluid out. If there's a lower amount of pressure, it's gonna push less fluid out. But when a normal person, hydrostatic pressure is 30 millimeters of mercury, it's gonna be pushing out fluid, or contribute to pushing out the fluid. There's also BCOP, that's B, can't remember what it stands for, colloid osmotic pressure. That has to do with albumin, because albumin is big, it's a colloid that's big, and it can't pass through this membrane. So if we have a buildup of albumin inside, if you remember, if we have a high concentration, low concentration out here, let's say a low concentration of solutes, high concentration of solutes, water is going to want to move in to even that out, because if solutes can't pass through, if they're not permeable, water through osmosis is going to move through and balance out the concentrations. Another one, interstitial colloid osmotic pressure. We can have little proteins out here. By the way, this is inside the capillary. Outside the capillary is the interstitial fluid. I think you call it, this is like the blood. That's why I have a red blood cell right there. Can't really see with the light, there's a red blood cell. And these are cells right here. And it could also be cells, there are cells on this side, but I just didn't draw them. But for this one, if we have, again, kind of like this one, but the opposite, if we have solutes on the outside, these proteins which can't pass through, if we have these proteins, water from the blood to even it out is going to come out, because there's a low, let's say there's a low concentration on the inside of solutes, high concentration on the outside. Water is going to leave the blood into the interstitial fluid to balance that out. We're talking about these all kind of individually right now, but eventually we're going to talk about how they're all combined to create one movement of fluid. This one, the IFP, is interstitial fluid pressure, I think. But that has to do with a, what is it called? Glands. Something to do with glands, I think. And it's a system, the system that has to do with the lymphatic system. Lymphatic vessel. This is a lymphatic vessel. This is constantly sucking in fluid, bringing it to the lymphatic system. Because it's sucking in, it's acting as a vacuum because it's sucking out here, and it's not going to have a direct effect. So it's not directly sucking this in, but because it's sucking this fluid in, it has an effect, kind of a vacuum effect, sucking fluid out from the blood, the capillary, into the interstitial fluid, and that's how that works. These all have different numbers. Hydrostatic pressure, 30 millimeters of mercury. Interstitial colloid osmotic pressure, 8 millimeters of mercury out. Interstitial fluid pressure from the lymphatic vessel, that has 3 millimeters of mercury, bringing stuff out. That's actually kind of better lighting, I think. But this one is the only one bringing stuff in, and this is the one with the albumin. Albumin can't pass through. I have a lot of albumin in here. Concentration of albumin is greater inside of the solutes, so water is going to move from the interstitial to the inside of the capillary. But let's add this up to show you how, when it all combines, it actually means something. So right here, we're going to have in. Here, we're going to have out. So what do we have coming in? We have 28 millimeters of mercury of BCOP due to the albumin. 28. Out, we have 30 from hydrostatic pressure. We have 8 from ICOP. And we have 3 from IFP. So this equals 41. This equals 28. And then we're going to subtract them. And this gets us, let's see, 13. So, and which number was bigger? It was the out. So we have 13 millimeters of mercury pressure going out. So overall, I could draw a big arrow. Kind of don't want to because I don't want to ruin my drawing, but I'll just do it anyways. I'm just going to draw them in black. I feel like you can see that maybe better. Don't get mixed up. So we have and this is that 13 millimeters of mercury going out. That's when we combined everything. That's what we have going out on the arterial side. Let me come over here, and something changes. It's the hydrostatic pressure. That's the only one that changes. Everything else stays the same on the venous side. And the reason why this one goes down, I'm trying to remember, I want to say it's just moving down this lane, and as it's moving down this lane, it's losing kind of momentum and pressure, so it drops down to 10. So the dropping down to 10, that's always going to change our numbers a little bit. Now it's getting really dark. Turn on the lights. Okay. So now we have still coming in. Only thing that changed was HP. Still have 28 coming in from BCOP. Still have 8 going out, ICOP, 3 going out, interstitial fluid pressure. But then HP is different. We have 10. So what does this equal? Still have 28 on this side. And over here, is that 22? Let's see, 8, 11, oh, it's 21. Okay, so we subtract these, we get a number, which is 7. Which number is bigger? It's the N number. So now, we have 7 millimeters of mercury coming okay? And that's on the venous side. Something that could change these a little bit is, talked about a little bit before, if we have a really high blood pressure, I think it's like systolic, oh, what is it? I think it's diastolic over 160. I can't remember, something over 160. I think it's the diastolic over 160. Super high. Blood's coming in, the sphincters can't stop it. It's being overpowered. HP is gonna go up. If we have HP go up, we're gonna have a lot more going out. So that can cause edema. Edema is buildup of fluid in the interstitial space. Over here, we can kind of have the same thing. If we have a venous block on this end due to, just some sort of blockage, probably some other things, but we're just going to talk about blockage right now. That's all I can really think of. But if we have that, let's say a blockage, and there's pressure's not being able to push as much through over on this end. I think at right side heart failure is another one too. But it's going to cause a buildup of pressure if there's a blockage down this way, to the venous way, towards the venous, towards the heart on the venous side. So let's say that increases our HP. Let's just say a little bit. Let's just say it's like 15, right? That's gonna change it by 5, so that's gonna make it just 2 millimeters of mercury coming in. And so that's like less fluid coming in now, so that can lead to a buildup out here. There's less fluid being pushed in. And let's say it was even higher, like kind of back what it was over here, higher to the point where now we have a higher number on this side. That's gonna be bad because then we're not even getting water in here or fluid in here, and so that's bad. Usually, healthy individual, this is at 10. There are a couple things important about this because we talked about edema, that's buildup of fluid in the interstitial space. A couple things can cause this. Hydrostatic edema. What is that one again? That's kind of what we just talked about. That's super high blood pressure over here. Can't remember if it's diastolic or systolic over 160. It's got to be, I think, diastolic, because I think they said they're resting. So diastolic over 160, super high, blood coming in. It's pushing on this side of the vessels a ton, and that's going to increase the hydrostatic pressure, pushing more fluid out. That can lead to edema. Other one for hydrostatic is the blockage over here. The blockage can increase this, let less come in on this side, build up of fluid in the interstitial space. Next one is permeability. This is kind of has to do with kind of like BCOP or ICOP, because that's the osmolarity. And they mentioned trauma with this one. So if someone has a burn or a bad scrape or kind of different stuff like that, but I think a burn is a good one. That can mess with these cells. This can open up the cells and allow more proteins like this to come in. If we have an increase in proteins, we have a lot of increase in more solutes on this side. So there's higher concentration of solutes on this side. So water is going to come out to the area of higher concentration because the solutes can't go through, but the water can. So buildup of water on the outside, buildup of water on the interstitial fluid. That can cause edema that way. Osmotic edema, that's a little different than this one because this one's more talking about the plasma and the blood in the inside. If the blood in the inside, if it's low osmolarity, so less solutes, even if there's not a buildup out here, there's more solutes because it's not kind of at equilibrium, I guess. And so like, let's say like this one's at 300 out here, but this one's at 250. That's going to cause water to want to move out because there's a more higher concentration of solutes. So that's the osmotic edema. Lymphatic edema. That has to do with this guy up here. If this guy gets blocked or damaged, the lymphatic vessel, like we kind of talked about, it's sucking in. So it kind of creates the vacuum effect to suck water out of here. if this guy's not doing his job and taking stuff in, then let's see, what does that do again? This is gonna create a buildup of fluid out here because this guy's not sucking in its 3 millimeters of mercury, so it's gonna create a buildup. There's another cool thing too. I remember, I think it was in class we talked about how I think it's because we have 13 millimeter mercury going out, 7 going in. That creates a difference of like 6, and I think that, or like 6 kind of. I think that is made up by the lymphatic vessels. So that's, if that makes sense. I can't explain it super well because I don't know exactly, but that plays a part, and it's important we have the lymphatic vessels because it helps keep it all balanced. And it balances out the difference of 13 going in, 13 going out, 7 coming in. But yeah, that's the video for today. For this unit, that was unit 3, essay question number 2. Yeah, a lot easier this essay question. Not a ton of stuff. Thanks for watching.